Okay, let's get started. Good morning and good afternoon, everyone. Welcome to today's Adams webinar titled Dynamic Loads Prediction for Wind Turbine Systems. My name is Yijun Fan. I'm the Product Marketing Manager for Adams and EZ5 at MSC Software. I'm based in our California office in the USA. Today's presenter will be Christoph Reichor. He is our lead application engineer based in Germany. Christoph has been a long-time Adams user and an industry expert in many areas. In today's webinar, we are going to talk about mainly the Adams solution for the wind energy industry, specifically a highly customized toolkit that we developed for modeling and simulating the wind turbine systems. At this point, I'm going to pass the presenter to Christoph.
Yeah, good morning, good afternoon, and good evening everywhere you are on the world here. Many thanks for joining this webinar. As Yijun introduced my person, my name is Christoph Reichor. I'm located in Alsenau. It's a small city nearby Frankfurt in Germany. I would also like to introduce my colleagues Joachim Beuse and Monika Schott, which are key developers for the tools I now would like to present. So the load prediction is not everything in this topic. The topic of wind turbines is more than only the loads. It's the structural behavior, it's the noise, it can be fatigue. So we will just discuss all these different topics during this webinar. So the agenda foresees the design processes. To give you just an idea, what is a typical design process and what could be an ideal design process. In the second point, we will clarify what is AdWiMo. AdWiMo is the main tool for the turbine modeling based on Adams. We will also explain what is CE, the so-called certification engine, which is the system around AdWiMo to help you to come very fast to successful simulations and reporting for your certification purposes. And at the end, we will have a summary and you can ask questions if needed. As said before, we have got two steps here in the agenda. The first one is AdWiMo, and AdWiMo is the tool based on Adams purely there to define the master model. This means with AdWiMo, we create one wind turbine model, and as it is usual for numerical simulation, of course, one model only can handle one load and boundary condition. And therefore we need a second step, the certification engine. And the certification engine takes this master model, puts a lot of boundary conditions around, creates thousands of model variants of this master turbine, is administrating these thousands of variants, is generating the simulation jobs and is running these jobs and is extracting results and so on. So we have simply said two effects. One is modeling and the other one is handling the model. If you are looking at a typical process, I think it's similar everywhere on this planet. We have got a specification coming from the customer. You've got a turbine that is designed to be at a certain place. You've got special wind conditions and so on. This is boundary conditions coming from the environment. So you have to perform the load calculations. You have either to create a new turbine or you are creating a turbine based on an existing design. Doesn't matter, however you do it, at the end you want to see the loads in the system. You need the loads for the components. Components are the things like the blades, the main shaft, the main frame, gears, bearings, whatever you are using in your wind turbine application. The loads are needed for these components to give a rough estimation what will the behavior be and what will the lifetime be. In many cases, you are using the DIN or ISO lifetime calculation. This means you have got a component, you have got an analytical description of your component, you have the loads, and you get a statement with respect to your lifetime. You can do it also the numerical way. You can use your loads, and FE is a very common method to describe the structural behavior of applications. So you can use your load, you can apply it onto a more detailed model, FE model, of your component. Here, the picture shows gears, could also be, of course, a housing or the shaft or whatever. And you apply these loads to get a more deeper insight into the stress distribution of your component, to evaluate the durability of your component. In the next step, can be the case, doesn't have to be the case, depends on your situation. You can perform a fatigue simulation, which means you take the results coming from the durability calculation, mainly the stresses, and you perform a fatigue analysis to get the lifetime of the part via a numerical approach. This is an opposite of to the analytical approach I showed at the beginning. Mainly static simulations are done with this, but you can also perform, of course, dynamic simulations. For example, if you look at the vibration of the systems, in this case we see a housing, so you can look at the vibration of the housing, and with the vibrations you can perform a fatigue simulation on one hand, but on the other hand you can perform a real acoustic simulations where you get the sound pressure level in the air, for example, to get the acoustic you can hear really. This is valid also for the housing, this is valid for the blades, for whatever component which is of your interest. All these simulation steps are performed in a sequence. That's an advantage and a disadvantage at the same time. Advantage is, of course, you have got every step under full control, you know exactly what happens. You've got an input, you have got your solver, you've got your output. The disadvantage is clearly everything has to do serial. So this means you need some time to perform the complete process. And of course, you have to transfer data from one solver step to the next solver step. Transferring data always means converting data with a certain probability to make failures during the conversion. And at the end, after you have done all your simulations, you have to create the reports. And what we learned so far in the past is creating the reports needs a lot of time. You have to extract all the relevant data from the various simulations, and you have to put it in a report. And the problem starts if you change something in your system, you change a component, the design or the loading of a component, you have to redo all the steps again. And as you are transferring data mainly manually from one solver discipline to the next, you always have to lay your hands on this process and have to change it manually and so on. So it takes you a lot of time to go through different iterations. The ideal process would look a little bit different. You start again with the specification, that's clear. You need an engineering knowledge or you need a concept for your turbine, could be also again existing design or a new design. But then the ideal process would be a simulation which covers all the topics in one single simulation. In one single simulation means in one model. That's clearly not possible. If you look at the different solver disciplines we are covering, acoustics, multi-body dynamics, FEM, it's clearly not one solver. But if we are not able to put everything together in one solver, perhaps it's possible to create an automated process chain. And this would be the big difference to the process before. So we try to perform simulations in parallel. If we are not able to do it because the solver are so different, then we need an automated process to perform the serial simulations automatically. This would then, of course, save the time you need to convert the data, and it would simply save the user's time because the work is done by the computer. That's the principal idea, and this is what MSC is trying to achieve and what we are working on. At the end, we have the reports. The reports, again, something special. Report means we have to extract the data. So if you know which data you have to extract, you can create an automated algorithm which does it for you. The problem always starts if you have different results in different simulations. If you want to be very flexible, then of course it's counterproductive for an automated report. But if you are working in standards, This means a standard according to certain guidelines you are using, or against internal standards, then this process can be automated. And everything put together in one, let's say, in one hood would mean we have a simulation. The simulation is based on a selected norm. The norm, again, can be also an internal guideline, and everything is fully automated. This is the principal idea of the ideal process chain. What we do at MSc is we created AdWiMo CE. AdWiMo stands for the Advanced Wind Turbine Modeler, while CE stands for Certification Engine. This is a process. It's not a single software. It's a process. We are combining several disciplines. We try to put very different solver in a chain, but in an automated chain, so that we are able to consider the wind loads, the wave loads, a more detailed drivetrain, and all the structural behavior within AdWiMo, so that we say our model covers all influences that are relevant for the structure. And the certification engine says, okay, how do I have to modify the loads on this structure to fulfill all the requirements of my guideline? This means at the end, the certification engine takes the master model, so we call it the master model what we create in AdWiMo, and is modifying it, is simulating it, is extracting results, and is using the results to generate a report. So this means at the end, if you look at MSc AdWiMo, which is the basis, the first step, how we call it at the beginning. AdWiMo is based on ADAMS. ADAMS is a multi-body system, multi-body dynamic system, and it's known in the industry for the high accuracy and so on. It's very efficient. And the key point is here underlined. We consider the whole turbine, including the wind, the waves, and the foundations. As said before, if we are dealing with multi-body dynamic system, we only can treat one load situation. This means we have got one wind from one direction. We have one type of wave and from one direction. But if we look now at AdWiMo, what it covers, we see it's a quite complete system. We can handle the flexible blades. We have got a flexible hub. We have the waves, as I said before. We have gears. You can choose if you have got simplified gears, if you have got high accuracy gears. We can handle the generator behavior. This can be a very simple torque velocity curve. This can be a more complicated system. We have roller bearings. This can be from a spring damper system till a really detailed bearing system, which includes FE effects and so on. We have the mainframe, we have the tower, we have the subsea structure, and we can have the soil to found the turbine in the ground. We cover also the aerodynamics, the controller, and the hydrodynamics. It's seen here as separate points because this is not a core competence of MSc. MSc is strong in all topics related to structural behavior. And for aerodynamics, we have got open source course used, Aeroden. And for controller, of course, every turbine designer gets the controller either from in-house or this is an external component from a supplier. In most cases, the controller is a hidden component which has to be used, but you don't know exactly how it works. So we use it as a kind of black box within AdWiMo if we don't use our own generic controller. For the hydrodynamics, we have a tool called C-Loads from our colleagues in Sweden. It was mainly created for other offshore applications, but could be used for the turbines. So we have integrated it to be, let's say, 100% perfect fitting to ADAMS because it's also based on ADAMS. Currently, we are still in the environment of atoms. Everything here is pure atoms technology. It can be used 100%. There's no need to use another solver, so it's very efficiently, and it's, if I want to use the word parallel, everything done is in parallel. So the wind loads, the hydrodynamic loads, the controller situation or the controller behavior, and the mechanical systems, they are interacting, they are solved at the same time. But there are more effects probably we would like to cover, and one of them is fatigue. Fatigue is, of course, another solver discipline. So this means in this case we now come from a parallel processing to a serial processing in an automated process chain. This means if we use the standard atom simulation, we get the vibrations or the movements of the nodes on the surface of the structure. This could be tower plate or gearbox housing, for example. And then we use this as an input for the fatigue simulation. But the key principle here is the user doesn't need a manual interaction. This process is set up automatically. So this means the data is converted automatically, which means we don't make any failure. Also, the subsequent simulation of the fatigue solver is parameterized in a way that is stable and accurate at the same time. So it takes a little bit more time because it's a pre-processing seen from this point of view, but it doesn't take time for the user as it is done automatically. The point is that the user should get an insight about the fatigue behavior right at the beginning of his design, because atoms normally is used at the beginning of the design process, and therefore you can check or evaluate a big variety of different concepts, and all the time you can perform immediately a fatigue simulation to get also an evaluation of the fatigue behavior, which is normally in the typical process chain a step which is quite a bit later than the original concept design phase. So very often at the end of the process someone says, oh, the fatigue behavior is not good, let's change something in the concept. And this, of course, takes a lot of time. And this is what we try to avoid here. And the same is valid for the acoustics. Acoustics is, of course, a high-end solver discipline. But at the end, we get the vibrations coming from the structures. We have, meanwhile, an automated mesh creation for the acoustic space around this structure. So we can use the input coming from atoms. It's directly transferred to Actron, which is our acoustic solver at MSC, and you can get the acoustic. The acoustics is the sound pressure that you can hear in the acoustic space. Again, this is a serial process. The acoustics is also seen as a kind of post-processing for atoms, but it's automated. This means there is no user interaction needed. You simply can wait for the result, which is given by your computer. The solver settings, for example, in this case, they are of course set as a default. This is our experience at the end. But as we are using a real input tech for acoustics, as we do, for example, for fatigue, a specialist always has the chance to take this input file and to modify it in order to get an even more accurate result, if needed. Sometimes this is needed at the end of the design state, but if you are in the concept phase, the acoustics and the fatigue shown here are mainly used to get an impression about the following steps. AdWiMo itself means, okay, I take several disciplines into atoms. As explained before, we have the aerodynamics, and we are using as a standard the annual aerodyn code. It's a proven code for the wind load calculation, and this wind loads are applied onto the blades. For the controller, either we can implement the specific controller coming from your supplier or create it in your house, or a user, if if he hasn't a chance to get a specific controller, he can use a generic controller which is delivered with AdWiMo to play a little bit around with. For the wave generator, as explained before, we have got MSc C-loads. MSc C-loads is Adams functionality. Therefore, we have a perfect exchange of data between the turbine structure and the subsea structure, which makes the solver very, very efficient. The components, as explained before, it's the blades. We have the nacelle, and the nacelle is a key point for subsequent simulations. You always can describe the components in the nacelle as simplified structures to keep the simulation time very, very high. This is important if you are talking about certification load cases, if you are talking about real time. So if you are talking about 10,000 load cases, it's better to have simplified nacelle ingredients, I would say, in order to get fast simulations. If you are more interested in a very realistic and a very detailed behavior of your nacelle, and you are not performing 10,000 simulations, if you're only looking at 20, 30, or 40, then it's perhaps also an opportunity to get a more detailed description of the, for example, drivetrain within a nacelle. Tower is a typical flexible body, as usually used in Adams. It's normally represented as an MNF file, as a flexible body including the shapes, or we have a so-called tower by beam representation, which uses a Timoshenko beam to have also a nice representation of the tower. The foundation and the soil is included in that way that we have got a certain connection between the turbine itself and the ground, which covers a little bit the different types of ground you can have. So it's more a sandy ground or a fixed ground or whatever. At the end, this is what you see in the bar at the right side. We take the results and filter the results. As you can imagine, if you have got thousands of simulations with Adams, you get a huge amount of data. And if you are distributing this amount of data in a network, it would take you a long time. So what we do is at every computer which is simulating model, we filter the data to give back only the data which is really relevant for the results visualization, to keep the network traffic low and to reduce the data you have to manage in general. If you're looking at the Windloads, we have the Aerodyn wind code is an open source code, so it's free to distribute it with Adams together. As you can see on the arrows or the blades, we have the flexible structure of the blades, and therefore we have a changing wind loads depending on the position of the blades and depending, of course, on the structure of the blades. This is just one possibility to apply loads. First of all, the system, the AdWiMo system, is an object-oriented system, so we can exchange data, or we can take some components out and put some other components therefore in, which means we have now used the Aerodyn code, but also we had tried to implement the ECN code or whatever, so we can switch the wind load code. This is depending on the customer and its preference. At the moment, as is. We also can use the connection to a CFD code. As you probably know, MSc Software now owns a tool called Cradle, or a company called Cradle, and they have a special fluid code. It's not connected at the moment, but if you are interested, and you are not interested for certification, of course, because the simulation time would take too long, but if you are interested in a very detailed analysis of your blade behavior in combination with the rest of the structure and your turbulences of the wind, then a connection to a CFD code can be your choice to get a deeper insight in the behavior. This is not done at the moment. This is just shown to explain that we have the capability, if needed, to connect a CFD code. For the wave loads, we use this MSCC loads. The MSCC loads is based on the Morrison equation. At the moment, the solution, the Morrison equation means the wave have an impact on the structure, but the structure doesn't have an impact on the waves. This is the first attempt we made. This is included, and it works for floating structures also as for fixed structures. Currently, we are working on a solution to have the shapes of the subsea structure, so that really the shape also has an influence on the waves. So the first prototype is existing. Perhaps it takes a little bit time to have it in the release of the software. At the end, this very important sentence is the third one, the fully integrated into atoms, no co-simulation. This is very important because a weakness of the connection between atoms and another third-party code is that you have to hand over the data, and handing over the data always needs time. So everything is done here in the main memory, so it's really fast to hand over the data from the subsea structure to the turbine structure. The structural components are as usual as in Adam's the common ways. So we have the MNF files, the flexible bodies, can be a linear flexibility. Meanwhile, you could use a non-linear flexibility. Of course, then the simulation time would increase. But at the end, you can decide on your own which type of flexibility you want to investigate, or which one should be considered. In general, the linear flexibility in the MNF files is enough to represent the deflections of the structures, for example here, like the mainframe or the support of the main shaft. One special topic is the drivetrain itself. That's the reason why I put 2 slides for the drivetrain here in this presentation. Normally for your certification loads, you don't need a perfect detailed drivetrain. The drivetrain is in most cases simplified because you are interested in the overall loads of the turbine. But of course, you can use your loads coming directly from the blades to evaluate your gearbox. And therefore, you need a very accurate gearbox, because the blades have, of course, not a linear load. It's a non-linear and it's a vibrating load. And this has an influence on the lifetime of your components in a drivetrain. And we have got 2 solutions called Gear AT and Bearing AT. AT stands for Advanced Technology. And with this, we have got a fast and accurate possibility to get insights about this component behavior. So, for example, you get the flank pressure on the teeth, you have got the flexibility of the teeth, you have got the flexibility of the bearing, you have got the load distribution within the bearing. This means on every roller, you have got load distribution in the gears, all connected with the flexibility. So it's an accuracy that can be used to design really gears and up to a certain detail grade bearings, if needed. And just to visualize this, if you look at this movie here, and you can see on the right side these curves. This is at the end the force. That upper one is the force on the rollers, and you can see there are different rollers in the diagram, and the load is not constant as normally assumed. If you are using the analytical approaches, the load is really vibrating. The load is changing. You have got longer frequencies and shorter frequencies. At the end, this will have an impact on your lifetime. And if you look at the graph at the bottom, it shows the misalignment, and you can see there are some peaks. So in a static simulation, there would be a flat line. If you look at a dynamic simulation, you see this peak, and every peak means a stress load onto the component. So if you want to have more details about a drivetrain, you have the possibility using Gear AT and Bearing AT to get a very, very deep insight in the excitations of your system. So at the end, you get an excitation due to every roller in the system, if you want to, and you get the excitation due to every tooth in the system, if you want to. And as always in the simulation, you have to decide on your own how detailed does my model have to be? But you have the capabilities to be very detailed. Second step, and now I have got much less movies because the second step is very unspectacular. It's just the administration of the master model, which means AdWiMo CE, the certification engine, is nothing else than a mask that says, okay, I take this turbine, I take this guideline, I take this environmental conditions, for example, the site-specific information for the turbine, and then perform everything automatically. This is what we see here at the end. We have here the CE mask. We select the norm. We select the turbine, which is formally created by AdWiMo, of course, but we don't touch it at this time. We simply select the turbine we want to use. Then we start the load generation. All the different models are created. The different model means if you change the wind, it needs a different model. If you change the wind direction, we need a different model, and so on. That's the reason why we come to thousands of different models. And after we have done this, we can simulate it. We can distribute the simulations in the network. And at the end, from the network, we get the results back to create a kind of report. And if we look at the current capabilities, we have various guidelines already incorporated. So, of course, if you have got other guidelines, it can be incorporated. It's just a type of programming. It's a manual work to do it. The concept we are using allows to create or to introduce many more different guidelines. We select the turbine. The turbine is created by AdWiMo. AdWiMo generates a full set of files, and the so-called ATW file is the main file. And if you select this one file in AdWiMo CE, then you get all the other files also to get a complete simulation setup. We have the settings for the site. The wind turbine classes can be chosen. We have the wind probabilities, wind speeds, and so on. And all these type of things are firstly set according to the guideline, or if there are any default values available, then these are set. But always the user can override his existing data. He can store his existing data and can use it again, of course. We can create many different variants of stepping. For example, if you want to have the wind growing from 1 meter to 5 meter in 1 meter steps, you also can introduce then instead of 3, 4, 5, 3.5. So we have got a system which allows you to be very flexible with your input data to allow you only to ensure that you are able to calculate only what you really want to calculate. That's very important. This is also just the settings. So for example, for the wave settings, it's the same. You can change the wave for every load case. You can use standards. You can override it. You can create own waves. You can create own loads anyway. So we are very open. What we try to cover in the masks, in the general GUI of CE, is that we provide the standards, and the user is allowed to override the standards, and not only to override the standard as a complete block. We allow to override the standards per load case. That's the principal idea behind. And then we have got the special things like controller settings or starting conditions of the turbine. Everything is done in the same format. Very important to say, we have got a copy and paste to Excel or to a CSV file. So if you create these type of tables outside with a third party program, because you have got an own automated process already in place that creates these types of input files, normally we can use them if you know the format. Very important is this point now, it's the user DLC. So if we have got the standard guidelines, we create a certain set of load cases. but normally every company has also own load cases, and we are able to create these own load cases via Atoms. So you create your load case in Atoms, but then you can use this load case in CE as it would be a standard load case. And the same is for the requests. If you have gotten a request which you normally use to evaluate behavior of your turbine, and this request is not a standard request, you can create a request in Atoms, and then you can use it in CE as it would be a standard request. That's a very open system, and therefore we are able, let's say, to perform every type of load case you want to perform, as long as it is doable with Atoms. And I only can say many things are doable with Atoms. If you are talking about a network, this is a very complicated thing to ensure that if you are dealing with 10,000 load cases, that they are perfectly distributed in the network and that not a single load case gets lost somewhere. And we have got a setup that is normally made by your IT administration to say, okay, how many CPUs are used, where are the CPUs located, and where are the scratch directories located. Once you have done this, you can use it. You don't have to touch it anymore. If you have to change it, if you want to change it, you can read in a configuration file, can restart the analysis manager, and you can use your new network. This means in some cases it's necessary. For example, if you want to perform all certification simulations, you need 100 or 200 CPUs. But if you're only testing certain concepts, then probably 2 or 3 CPUs are enough for you. Or they are even more, perhaps they are locally used. So we have got a chance to be a little bit more flexible. And this is what it looks like. So we have got the main local host, which is at the end the computer of the user. Here we have CE. CE is administrating all jobs. And all the different CPUs around, they are distributed in networks. They are just there to calculate. Important is, if you look at the left corner at the top, the recovery functionality. If we are working in a network, of course, it can happen if you have got a power down somewhere or you lose your network connection. We implemented a functionality that allows you to recover all the jobs manually, which means you have got a button, you push this button, and then AdWiMo CE goes through every planned job, is looking into the cluster, if this job is existing, what data is existing, what is the status, and so on. So it allows you to give you a full picture of the status, where is your certification simulation. This is very important. Depending on the capabilities of your machine environment, your simulations may need from 6 hours to 3 or 4 days. So it's depending on your system. And the very important point at the end is the result visualization. So if you are calculating in a network, in a cluster, you are creating a lot of results. They are reduced, as I explained before. They are transferred back to your local machine. They are gathered, they are assembled, they are prepared somehow, and now we want to see something on the screen. And you have got 2 possibilities. You can look at the results as you usually do in Atoms Post. This means you see the structure moving, and you see one certain load case. You can evaluate the behavior of one certain load case. On the other hand, we have got a report. It's an automated report, and the report is created according to the standard you have selected before. Of course, we know there is not an out-of-the-box solution because every company has their own way to create these reports. But what we did is to define an object-oriented way of creating these reports, so we can always introduce new components, new tables, new curves, or whatever. So this is a very modular setup. So we provide, let's say, a base, a template for a report, and according to your company behavior, we can adapt this report to fit perfectly to your to your common behavior and your common feeling. This is how it can look like. It's just an example to give some nice pictures. So we have everything in. We have got curves, we have got table, we have a Campbell diagram, and so on. So the modules are all there. If someone needs something which is not in, it's not. Normally, that's our experience. Quite easy to implement, and this is what we also offer. If someone is using our tool, that we adapt the tool a little bit to his expectations. If you need, for example, a curve which is not already existing, you are able to create this curve. As mentioned sometime before, you can create your own requests within atoms, which means it will become an absolute standard result. But then you are also able, in the result post-processing, to create curves out of this result. So if you have got a new result, then of course it's not part of the standard, but you would like to have a diagram, then we have got a kind of diagram generator which allows you to select requests and create diagrams. The setting of the diagram, here called the default RTP, is stored, and we put it into the report, and the report then takes this drawing and shows it in the report. And so you can create combinations of curves, you can create different diagrams, different types, and so on. So we are quite free to expand the standard report to a very, very highly customized report. Post-processing, we always can decide, do we want to see just a curve, a request? Do we want to see the model with results? Or do we want to change the model? This is what we here call review. So if you have got, for example, a model which really does not converge, normally the models converge, but from time to time, if you have thousands of simulations, you might have a simulation that doesn't converge for whatever reason. You can open this single model. It's shown, the analysis manager shows exactly which model has a problem, and you can change something in this model, and you can rerun it again to get a result to be used in the report, for example. So now time's over. Let's come to the summary. What I would like to emphasize here, and what was also the purpose of the explanations before, with AdWiMo, so the Atoms tool, we have the chance to simulate a wind turbine in a very high precision, as we consider wind loads, wave loads, and the complete flexible behavior of the structural components that are in this turbine. But not only this, AdWiMo also provides the results to perform automated processes in terms of post-processing, which then covers topics of acoustics, fatigue, or, if you want to, gear and bearing behavior. CE is the next level at the end, as AdWiMo is for one load case and for one load setting. CE is for the variety of different loads. So CE is taking the AdWiMo model and is creating all the simulations that are needed for certification or for creation of a report. This means this is, first of all, automated. CE allows you to administrate, so you can select only a few of these created load cases, for example. So the guideline says, for example, you've got 10,000 load cases, and you have got a certain subset, and the subset is only 20 of the most important load cases, and you calculate only these 20 load cases to save time, for example. We have the reports. The reports, they are according to standards, so it can be the standard guidelines, or it can be your internal guidelines. And also we allow the users in CE to create his own load cases which are not covered in a certain standard, and also to extract the results which are not covered in a standard. And at the end, this is the main idea and the main motivation which was behind this complete development. We would like to offer a comprehensive tool which allows you to substantially shorten your development and certification process. And the keyword here is really substantially. It's not reducing the time you need at a certain point a little bit. It's really looking at the whole process and lead the user very fast from the concept